So let's take a look at that now. And when I have rho here and mu, I should denote that that is for the liquid phase. So what I've done here, I've recast the Reynolds number with the mass flow rate, and I've also rewritten it with this capital gamma. And that is the mass flow rate in the film, which is a function of x, divided by the perimeter. And so the perimeter in the case of a vertical flat plate would just be b. In the case of a cylinder, a vertical cylinder, it would be pi times diameter, which we saw earlier. So that is one form of the Reynolds number. Now there's another form of the Reynolds number that we can come up with, and for that one what we do is we take this and we relate it to the convective heat transfer coefficient, and I'll show you how to do that in a moment here. So what we can do, we can come up with yet another Reynolds number, and for this one what I'm going to do, I'm going to use Newton's law of cooling. So we have some average convective heat transfer over our surface multiplied by A. This is a different A from the AC. This is the wetted area. So if you have a vertical plate like this, A would be that area there. So it would be that. And if you're looking at a cylinder, it would be the external area around the entire perimeter. It's not the cross-sectional area of the film, it is the wetted area. But that will be multiplied by the saturation temperature minus the surface or the wall temperature. And that is equal to m dot, so the mass flow rate, times the heat of vaporization, so going from a vapor to a liquid or a liquid to a vapor, and you get that out of steam tables. And one thing that I will say, be careful, because the tables often are in kilojoules per kilogram. You need to pull that out of that table in joules per kilogram or you're going to make mistakes. So don't make that mistake when you're pulling it out of the table. Make sure that you get it in joules per kilogram. And H bar here is average convection, convective heat transfer. And then finally, A is going to be the length, the vertical length. And so usually what we'll do is we will denote our vertical length like this. So it will be L times the perimeter. And remember I said the perimeter could be B in the case of a plate, or it would be pi times D in the case of a cylinder, where D is our diameter. Okay, so we have that. Now, what are we going to do with it? Well, we want to recast and write a new form of the Reynolds number. So what we're going to do, we're going to take the m dot from here and basically replace it with the m dot that is up here in that Reynolds number. So let's go ahead and do that. So this here, what I'm writing, is one of the important equations that you're going to be using. It's going to be heat transfer divided by the heat of vaporization. And we said heat transfer through Newton's law, we know that it's this. Divided by HFG. And when we plug in the mass flow rate, we get a new Reynolds number. So that becomes another form of the Reynolds number that we can use. So what we've looked at here are 3 different Reynolds numbers that you can use if you're dealing with condensation heat transfer, I should say. Where was the other one? The first one was right here. Okay, so those are 3 different Reynolds numbers, and then when we look at correlations, we're going to look at yet another one. There are many, many different Reynolds numbers that you can have when you're looking at condensation and films forming on vertical surfaces. What we'll be doing in the next segment is we're going to go back to this representation that we have here. And this was a starting point that Nusselt used, and he started with an object or a model that looked like this, and he came up with equations, and he went through dimensional analysis and came up with a way to be able to get the convective heat transfer coefficient. So that's what we're going to be doing in the next two segments, which will give us a form of the convective heat transfer coefficient. It won't be perfect because it's based on a theoretical model, and then we'll move in the next lecture to the correlations that are actually used, and so that's where we're going to be going.